welcome to this explainer. I am absolutely thrilled you're tuning in today because we are going to unpack something that is happening billions of times a second, all around the globe, yet it remains completely invisible to most of us. We are talking about the incredible behind-the-scenes engineering that keeps the entire internet from grinding to a screeching halt. Imagine millions of cars trying to merge onto a single highway at the exact same millisecond. I mean, it would be total gridlock, right? Well, the digital world faces this exact same threat constantly. So today, we're going on a proactive journey to uncover exactly how our networks prevent catastrophic digital traffic jams, specifically by looking at the fascinating mechanics of TCP congestion control. Okay, let's dive into this. How on earth does data travel across the globe without just completely overwhelming the network? It is a massive logistical nightmare when you really think about it. You click a link, you download a file, stream a movie, you are demanding data. But if the network just dumped all of that data onto the connection at once, it would overwhelm the routers, drop packets everywhere, and essentially just break the connection. To solve this, network engineers rely on a brilliant protagonist working quietly in the background, the TCP algorithm, which stands for Transmission Control Protocol. And specifically, TCP uses a highly structured congestion control mechanism to perfectly balance speed with stability. To wrap our heads around how this actually works, we've got to define our terms, starting with a very important acronym, CWN. This stands for the congestion window. Think of this CWN as the absolute hard limit on how much data the sender is allowed to put onto the network at any given moment. When a TCP connection first starts up, it doesn't just open the floodgates. No, it establishes an initial congestion window that is incredibly small, typically just 1 or 2 packets of data. It's literally dipping a single toe into the water to see how the network reacts before diving in. But wait, how does the sender actually know how the network is reacting? Well, that brings us to our next crucial concept, RTT, or round-trip time. The RTT is exactly what it sounds like, the duration it takes for that initial data packet to leave the sender, successfully reach its destination, and for the receiver to send an acknowledgement or an ACK all the way back. This creates a really critical feedback loop. The sender pushes a packet out, and then it waits for that ACK to return. This heartbeat, this continuous back-and-forth communication, is the foundational metric that is going to dictate the entire speed of our connection. All right, let's put these pieces together and walk through the mechanics of phase 1, which is called the slow start sequence. I really want you to mentally visualize these packets flowing back and forth. First, we establish the TCP connection. Second, the sender cautiously sends out those 1 or 2 initial packets, our starting CWND. Third, the sender waits and successfully receives those acknowledgements, those ACKs, back from the destination. And fourth, and hey, here's where the magic happens. For every single ACK received, the sender increases the congestion window size by 1 for each round-trip time. It's essentially rewarding successful delivery by increasing the sending limit. So the crucial point is the paradox here. Network engineers call this the slow start algorithm. But honestly, that's a massive understatement and kind of ironic, because the sender increases the window size by 1 for every single acknowledgement received. The growth isn't actually slow at all. By adding to the window for every successful round trip, slow start actually creates explosive exponential growth in the number of packets being sent. Let's visualize exactly how fast this scales up. Here we go. The connection kicks off, the congestion window is just 1. A single packet fires across the network. It successfully reaches the destination, the acknowledgement fires back, the round-trip time completes. Boom, we get that ACK back, so the window increases. We don't just send 1 packet this time, we send 2. 2 packets launch across the network, they arrive perfectly, and 2 acknowledgements immediately race back to the sender. And the window expands again. Because we got 2 ACKs back, the window doubles to 4. 4 packets blast into the network. Then it's 8, then 16, 32, 64. With every single round trip, the amount of data we are successfully pushing through this connection is doubling. The network is rapidly filling with this massive exponential wave of data traffic, hunting for the absolute maximum speed the connection can handle. But hold on, stop. We absolutely cannot double this forever, or we'd literally crash the entire system. And that is exactly why the algorithm hits a wall, the /thresh, or the slow start threshold. The TCP sender has a predetermined threshold in mind. Once that rapidly expanding congestion window reaches this critical pivot point, the algorithm knows it's getting dangerously close to the network's maximum capacity. It has to intelligently adapt right now or risk a total network failure. And this brilliantly illustrates the sheer genius of the overall TCP mechanism. Think of it like a comparison. On one side, you have phase 1, slow start, which is characterized by that aggressive, doubling, exponential growth. It's all about finding the network's capacity as fast as humanly possible. But on the other side, once we hit that slow start threshold, we transition into phase 2, congestion avoidance, which shifts the behavior entirely to a safe, sustainable, linear growth. We take a deep breath and shift gears from a wild sprint to a steady marathon. So let's take a collective breath and transition into this second phase, congestion avoidance. The explosive, crazy growth, it's over. The objective of this phase is completely different from the first. We are no longer trying to aggressively find the absolute ceiling of our bandwidth. Instead, our goal is to calmly, steadily maintain a sending rate that is actually sustainable for the network over a much longer period of time. Let's break down exactly how congestion avoidance achieves this stability. Basically, it shifts from exponential to linear. How? By incrementing the congestion window by just one single packet for an entire round-trip time. Instead of doubling the window based on every single tiny ACK, it waits for the whole batch of packets to be acknowledged, and then simply says, okay, let's just add one more packet to the total load next time. This meticulous linear increase prevents the rapid packet growth we just saw. It gently probes the network's capacity, maintaining a highly sustainable sending rate without suddenly choking the intermediate routers. But hey, the real world is messy. Networks are wildly unpredictable. Even with our cautious, linear congestion avoidance in play, eventually the network will reach its absolute physical limit. Suddenly, bam, crisis detected. A router somewhere along the path gets totally overwhelmed. Its memory buffers fill up, it literally can't handle the incoming data, and packets just start dropping into the void. Or the routers might actively send back congestion signals. The sender realizes that expected ACKs are missing, the network is officially choking. When this happens, TCP doesn't just stubbornly keep shoving data into a clogged pipe. No way. It executes a rapid, fail-safe reset. Step 1, the congestion signal or packet loss is detected. Step 2, the algorithm triggers a massive self-preservation reflex. It drops that congestion window sharply, potentially crashing it all the way back down to an initial window of just 1. Step 3, it completely abandons congestion avoidance and re-enters the slow start phase. It clears the traffic jam by instantly stopping the flow and then starts the whole discovery process over again from the very beginning. Which brings us to this perfect summary of everything we've just covered. These mechanisms work together to dynamically adjust the sending rate, ensuring reliable and efficient data transmission. It's this continuous dynamic balancing act, sprinting in slow start, pacing itself in congestion avoidance, and rapidly resetting when danger is detected, that allows TCP to navigate constantly shifting network conditions. It is not just a static set of rules. It's a living, breathing algorithm that guarantees our data gets exactly where it needs to go, as efficiently as physics allows. And that leaves us with this pretty wild final thought. Every single time a web page loads smoothly, every time your streaming video buffers perfectly in high definition, how many times did TCP silently adjust its window? How many times did it hit a threshold, shift to linear growth, or rapidly reset to save the network from totally collapsing under the weight of global data? It is happening right now, completely out of sight, keeping our entire digital world alive. Thank you so much for joining me to explore this incredible mechanism, and I really hope this changes how you view your everyday digital connections.